we can discuss another important flag that is basically called as the auxiliary carry flag or the A flag. Well, the A flag is very important in BCD or binary coded decimal arithmetic, right? And what is an auxiliary carry? Auxiliary carry is the carry out from bit 3 to bit 4 in 8-bit numbers, right? So this is bit 3 and this is bit 4. So if we have a carry from bit 3 to bit 4, then it means that we have an auxiliary carry. As an example, we can say this BCD 18 is there, 1 8, and this is BCD 28, 2 8, right? And we're adding these two numbers. Now of course when we add this 1 and 1 0, it's carry 1, right? So there's a carry from bit position 3 to bit position 4. This is basically an auxiliary carry. Now what is the significance of auxiliary carry? The significance of auxiliary carry is that if we have an auxiliary carry, the result of BCD arithmetic is incorrect. What it means that, let's say this we were adding this, so the result should have been BCD 46, right? But the result is basically 40 that is coming out, and this is because of this auxiliary carry. So whenever there is an auxiliary carry, we know that the BCD result would not be correct. So whenever we carry out BCD arithmetic, we check the auxiliary carry flag after the BCD arithmetic. So if there is an auxiliary carry, which means if this flag is 1, it means that there is an error. And how do we correct an error? Very simple. We just add a +6 always to our answer that we are getting. So we would be getting the correct result, which is 46 in this particular case. This rule holds true for all BCD arithmetic numbers. If you have an auxiliary carry, you just add +6 and your result would be the correct result. Now that should have been there. Then of course the sign flag holds the arithmetic sign of the result after an arithmetic or logic instruction executes, right? If sign equals 0, the result is positive. If sign equals 1, the result is negative. So for example, in this particular number, the sign bit is 1, right? So sign flag is 1, which indicates that the number is negative, right? Now over here the most significant bit of the sign bit is 0, which means the number is positive. So this is how the thing is done. And that interpretation, remember, interpretation would be done according to this bit position of the signed byte we already discussed previously. So then again, graph flag. Now this is the control flag, right? So now we are discussing basically the control flags. So one is the trap flag. The trap flag enables trapping through an on-chip debugging feature, right? So if we want to do single stepping, you want to stop after each execution of instruction, we can have this trap flag. So if t is 1, the processor stops execution for debugging. If t equals 0, debugging is disabled, right? So we can set these flags, right? Remember my discussion about command words that I did previously. It is like that. Then of course the interrupt flag. If I equals 1, processor responds to interrupts on the INTR pin. If I equals 0, processor ignores the INTR pin. Okay, so what are interrupts? Interrupts are basically events which are external to the microprocessor, right? So if we want the processor to respond to interrupts on the interrupt pin, right? This is active high, right? So if any device makes this INTR pin, right, which is this pin, which is INTR input pin of the processor high, it means that device is requesting an interrupt. But if I equals 0, processor ignores the interrupt pin. So if we have set the interrupt flag to 0, processor won't respond to this interrupt. Otherwise, if I equals 1, the processor responds to this particular interrupt. Then we have direction flag. Again, this is a control flag. So direction flag selects either the increment or decrement mode for DI or SI registers during string instructions, right? As I discussed previously, if we are using string instructions, right, string instructions are similar to, for example, memory copy function that you might have used in C language, C++ language, right? So memory copy copies from a source address to a destination address, right? So in assembly language, if we want to carry out memory copy, we carry out the string instructions. So whenever we are carrying out the instructions, we must specify the source address and the destination address. So as I told you before, the source address in a string instruction is specified by the combination of data segment register and source index register, right? And the destination address is specified by extra segment register in combination with the destination index register. So a string instruction, as has been described over here, would copy bytes from the source address to the destination address. This is the source and this is the destination. Now we can see if SI is incremented by 1 and DI is incremented by 1, the next source address would be higher than the previous address. Similarly, if DI is incremented by 1, the next destination address would be higher than the previous one. So this is the in direction that is controlled by the direction flag, right? So if D equals 1, DI and SI decrement. So if we set the direction flag to 1, after 1 byte is copied from source to destination, SI would be decremented by 1 and DI would be decremented by 1. But if we set the direction flag to 0, after each transfer from the source to the destination, SI would be incremented by 1 as well as DI would be incremented by 1. So afterwards we can look at the overflow flag. If overflow flag equals 1, it negates overflow condition in signed number addition or subtraction, and no overflow if overflow flag is 1. So overflow flag is basically important in signed numbers addition or subtraction. Let's look at the demonstration of a overflow in signed numbers. And what is an overflow? Indicate that the result of a signed arithmetic is unable to fit in the destination number format. For example, consider this 8-bit addition below. So this is a positive plus 127 number considering the sign notation, right? And we want to add plus 1 to it, right? So when we add plus 1 to it, you can see the 1 plus 1 0, 0, 0, 0, 0 and 1. Now this was the sign bit. Now this sign bit has become 1 as a result of the instruction. Now this 1 0 0 0 0 0 is minus 128. But we know that plus 127 plus 1 should have been plus 128. So because of this overflow, this result is incorrect and the overflow flag becomes 1 to indicate this particular error. Now one point, right? How can we avoid and how can we prevent this overflow error? Any suggestions?